In this lesson, we're going to look at how to use the roots of a polynomial, which may be complex or real or a mixture of the two. We use those roots to factorise it into linear brackets. Okay, so first I'd like you to just work out the roots to these three quadratics. You can either do that by using the quadratic formula, or you can complete the square and rearrange it, or you can use the quadratic solver on the calculator. They will all be complex roots in this case. So just pause here, and when you're done, unpause to carry on. Okay, so the first one has got roots minus 2 plus 2i and minus 2 minus 2i. The second one has got roots 3 plus 4i and 3 minus 4i. And the third one has got roots a half plus a half I and a half minus a half I. So you may have noticed there, in each of the three situations, we've got complex conjugates as the roots. So the real part is always the same in each of the two roots, but the imaginary part, one's plus, one's minus. So we know that any quadratic equation that's got real coefficients, in other words, if the coefficients of the original quadratic, a, b and c, if they are real numbers, there are only three possibilities for how the roots could work out. The first one is that you could get two real roots. That's something that we come across a lot in A-level maths. The second one is if you've got two repeated roots, so if it would be the same bracket twice when you factorised it, such as x plus 3, x plus 3, it would technically be just one root, but it's really the same root twice. And then this third scenario is the one that's happened up here, where we've got two non-real roots. And as long as we had started with real coefficients on our original quadratic, then those two non-real roots have to be complex conjugates of each other, as we can see above. So that will help us when we're trying to find roots. If we know that they're going to be complex conjugates of each other, it makes it easy to find them if we've found one. So we're going to look at how can we start with the roots and factorise the quadratic from that. We'll start with a real example that we're familiar with already. If a quadratic, if we know that its two roots are 3 and minus 5, then we know that the two brackets that it's going to go into would be x minus 3 and x plus 5, assuming that it's just x squared at the front, not 2x squared. So if we multiplied that out, we would find the quadratic x squared plus 2x minus 15. So that has come from taking the original roots, changing the signs of them both and putting them into two brackets. So we can do the same in the complex case. So for example, if we know that the root of a quadratic equation is z equals 1 minus 3i, and we know that the quadratic has got the form z squared plus bz plus c, and we are told that b and c are real numbers, then we can work out what the two brackets are going to be, and we can therefore multiply it out to work out what the quadratic is going to be. So because we know that 1 minus 3i is one of the roots, we know that 1 plus 3i will be the other root, because we know that it's going to have complex conjugate roots because it's got real coefficients. So we can write it like that. We can write it as z minus the first root in one bracket and z minus the second root in the other bracket. So it's a little bit more difficult to multiply this out. I'll do another example on the next page of how you can multiply it out using a grid, but you could multiply it out just using the way that you would multiply two brackets normally, first, outsides, insides, lasts. It just looks a little bit more difficult. You've got to be careful with the signs and such. So if you multiply that out, that will simplify down to give us z squared minus 2z plus 10. So that is the quadratic that had one root of 1 minus 3i and another root 1 plus 3i. So in this example, we want to factorise the quadratic x squared minus 4x plus 40. A quick check of the discriminant tells us that it's not going to have real roots. If we just do b squared minus 4ac, we'll see that we get minus 4 squared minus 4ac. Okay, so that is going to give us an answer that's less than 0. So we know that we're not going to get real roots here. I'm just going to solve this using the quadratic solver on the calculator, but you can do it using the quadratic formula or completing the square. So just by solving this, I've ended up with the answer 2 plus 6i and 2 minus 6i. So that tells us that if we wanted to factorise this expression, we could factorise it as x minus the first root, 2 plus 6i. You need brackets around that to make sure that it's minus the whole thing. And then the other one is x minus 2 minus 6i. So you may prefer to just multiply it out as we did on the previous example, or I'm just going to show you another method. Some people prefer the grid method when they're multiplying it out just to help keep track of all the terms. So if you wanted to use the grid method, the first thing I do is expand the inner brackets, so x minus 2 minus 6i, x minus 2, and that becomes plus 6i. You can then do a grid multiplying each of those terms together. X minus 2 minus 6i, x minus 2 plus 6i. If you multiply all those terms together, you're going to get x squared minus 2x minus 6xi, you get minus 2x plus 4 plus 12i, 6xi minus 12i, and then we get minus 36i squared. So it's a little bit time consuming, this method, but some people prefer it for accuracy. You can see that lots of terms will cancel actually. So for example, those two terms will cancel and those two terms will cancel. And some of the terms will simplify. For example, I squared is minus 1. So we know that because I squared is minus 1, this is going to become plus 36. So when we simplify that down, we're left with x squared, got minus 2x and minus 2x, so minus 4x, and plus 40. So that's just really to check that it actually does multiply out correctly. So that should give us what we've got at the top here. Okay, so the factorised version that we wanted in this example is that line there. That is the answer to the example. Underneath is just me expanding it to check that it was right. So for each of these 5 complex numbers, I would like you to work out if each of these were a root of a quadratic equation that had real coefficients. First of all, what would the other root be? Secondly, what would the 2 brackets be using the 2 roots that you've just found? And then thirdly, what would the expanded version of that quadratic equation be if you multiplied out the 2 brackets, either using the grid method that I did on the previous slide, or using the multiplying out 2 brackets method that I did on the slide before that. If you'd like to just pause the video and work out those things first, and then when you're done, unpause them. It doesn't matter whether you use Z or X really. This question is using Z because Z tends to be used more for complex numbers. But if you use X for your variable, it will still be the correct equation. So pause now, unpause when you're ready to move on. Okay, so A, if 4 minus 2i is one of the roots, 4 plus 2i is going to be the other root. So the factorised form will be z minus the first root, 4 minus 2i, z minus the other root, 4 plus 2i. If you then expand those 2 brackets using either of the 2 methods I've previously done, you'll end up with z squared minus 8z plus 20 equals 0 as the equation. For the second one, the second root should be minus 2 minus 3i, the complex conjugate. So the brackets will be z minus the first root, minus 2 plus 3i, and z minus the second root, z minus 2 minus 3i. So expanding that out will give you that as the equation. The third one is 5i. Because that's purely imaginary, the complex conjugate is negative 5i, it's just making the whole thing negative. So the 2 brackets will actually be z minus the first one, z minus 5i, and z plus 5i. It's so that is actually z minus minus 5i, I've just simplified it to z plus. So we end up with a z squared plus 25. That looks a little bit like difference of 2 squares, but with a plus in the middle instead of a minus, doesn't it? Right, part D, we get minus 6 plus 3i as the other root. So the two brackets are going to be z minus 6 minus 3i, z minus 6 plus 3i. So that multiplies out to give you that. And the last one, the fifth root should be 7 minus I, so we end up with z minus 7 plus I, z minus 7 minus I. That will expand to give you that. So if you're happy with that, you can actually skip the next couple of slides. I'm just going to go through a couple of those in slightly more detail in case anybody wanted any more example. Well, if anybody wanted just a little bit more explanation as to how those answers were found. So I'm just going to go through in a little bit more detail just in case anybody needed it. So as we said, if 4 minus 2i was one of the roots, the other root would be 4 plus 2i. So we'd end up with z minus the first root, 4 minus 2i. And the second one would end up with z minus the other root, 4 plus 2i. I'm going to expand that using the grid method. So first of all, I'm just going to multiply out the inner brackets. So minus 4 plus 2i, because it's minus minus. Z minus 4 minus 2i. So if I did a little grid method there, I get z minus 4 plus 2i, that's the first bracket. Z minus 4 minus 2i, that's the second bracket. Multiply that out, I'm going to get z squared minus 4z plus 2zi minus 4z plus 16 minus 8i, and then minus 2zi plus 8i, and then minus 4i squared. So just to simplify that, we can see that the 8i terms cancel and the 2zi terms cancel. Minus 4i squared becomes plus 4 because I squared is minus 1. So that is going to multiply out to give us altogether z squared. We've then got minus 4z minus another 4z, so minus 8z. And we've then got 16 and 4, so plus 20. So that is the answer to A, sorry. Okay, I'm just going to do question C because this one was slightly different. So as we said earlier, if 5i is one of the roots, minus 5i will be the other root because it's the complex conjugate. It's just the imaginary part made negative. So we're going to get z minus 5i as the first bracket and z minus 5i as the second bracket. So that becomes z minus 5i, and then z minus minus is z plus 5i, which is z squared. We're then going to get minus 5zi and plus 5zi, and then we're going to get minus 25i squared. So the two terms in the middle are going to cancel because they are opposites of each other. And then we've got I squared is minus 1, so that's going to become plus 25. So the final answer is z squared plus 25. So equals 0. That will be the equation that we needed to solve to get those two roots. So we're now going to factorize this cubic equation. The method itself is quite similar to the one that we would use in A-level maths with real roots. However, this is going to involve some complex roots. So we're going to start off with f of x equals x cubed minus x squared minus x plus minus 15. Well, first of all, we're going to use the factor theorem. We're going to show that f of 3 equals 0, and that's going to give us our first factor. We're then going to divide through by that factor, work out the other quadratic factor. I'm going to use that quadratic factor to help us find the three linear terms. So first up, we're going to just show that f of 3 equals 0. So just put all the steps in, 3 cubed minus 3 squared minus 3, that's 15. So So that gives us 27 minus 9 minus 3 minus 15. That does work out as 0. So we can conclude from that, therefore, x minus 3 is a factor of f of x. Remember, the explanations for these questions are just as important as the working out themselves, to make sure we get all of the explanation marks. So now that we know that x minus 3 is a factor of f of x, we can write this as x minus 3 multiplied by, we know the other bracket at the minute is going to be a quadratic factor, ax squared plus bx plus c. So we can find a, b and c by comparing the coefficients. So first of all, we can say, well, we know that that ax squared times that x has to equal x cubed. So that tells us that a must equal 1. We can also say that c times minus 15, sorry, c times minus 3 has to equal minus 15. So c must equal 5. You may have your own methods for dividing a cubic by a linear term. If you want to use a different method to this, that's fine, you'll still get the same answer. Okay, so we've got a and c, so we know that f of x can be written as x minus 3 times a is 1, so x squared, we don't know bx yet, plus 5. I'm just going to expand out those brackets, compare the coefficients with the original cubic to work out the value of b. So you could also do this using the grid method or using long division, it would work out the same. So I'm just going to expand this out. X times the second bracket gives me x cubed plus bx squared plus 5x. And then minus 3 times the second bracket, minus 3x squared minus 3bx minus 15. Then it's going to compare some coefficients. So I'm going to compare the x squareds. So I've got bx squared in my expanded version and negative 3x squared. So that's how many x squareds I've got in the expanded version. In the original version, I've just got negative 1x squared. So that tells us that b minus 3 has to equal negative 1, so that the coefficients of x squared are the same in both. So therefore, b must be 2. That tells us that f of x can be written as a linear term, x minus 3, times a quadratic term, x squared plus 2x plus 5. So finally, we've written f of x as a product x minus 3, x squared plus 2x plus 5. We now just need to solve that quadratic equation. Now the roots of that quadratic are minus 1 plus 2i and minus 1 minus 2i. So they are the roots of that quadratic there. So we can write that as 3 brackets, x minus 3, x minus the first root, minus 1 plus 2i, times x minus the second root, minus 1 minus 2i. So that is the that cubic written as a product of 3 linear factors. It's got one real root there and 2 complex roots. So finally, we're just going to factorize this quartic equation. Now you might think this looks quite familiar. Although it's a power 4, it looks a lot like a difference of 2 squares, because you have got 81 is a square number, 16 is a square number, z to the 4 can be square rooted, and we've got minus in the middle. So it is actually, as a starting point, a bit like a difference of 2 squares. If we square root the 81, we get 9. If we square root the z to the 4, we get z squared. We're going to have plus and minus because it's difference of 2 squares, and then square root the 16, we're going to get 9z squared plus 4, 9z squared minus 4. Now each of those 2 brackets will now factorise into their own 2 brackets. Now the second one is easier to recognise because it's another difference of 2 squares. So 9z squared, the square root of that is 3z. So 3z, 3z. And we've got plus 2 and minus 2. So that's just a classic difference of 2 squares. The first one is a difference of 2 squares but the complex version. So this is going to be 3z plus 3z minus. If we put 2i in at the end of each of those 2 brackets, that will actually multiply out to give us 9z squared plus 4, like we saw on an earlier slide. So you can multiply that out and double check that that does actually give you what we had originally. But that is 81z to the 4 minus 16 factorised into 4 linear terms, 2 that have got real numbers in, 2 that have got imaginary complex numbers in. So now please, if you could complete exercise 2A on page 33.